Hey everyone, welcome back to another AMC problem solving strategy video. My name is Sol, and today we're going to be going over another strategy that hopefully you guys can incorporate in 3D geometry problems. So I believe this problem is number 17 on the 2014 AMC 12A. So this just goes to show you that the AMC 12s during 2014 just had these ridiculous 3D geometry problems. But yeah, let's just get straight into it. So it states that a 4x4x8 rectangular box contains a sphere of radius 2, assumably this central one right here, and 8 smaller spheres of radius 1, so 4 up top and 4 down here. And it says that the smaller spheres are each tangent to 3 sides of the box, and the larger sphere is tangent to each of the smaller spheres. Okay, that's pretty useful. And it asks for h. Alright, so before we jump into the strategy that I wanted to go over, let's talk about what we already know about h. So, h can also be described not just as like the height of this box, but I mean, obviously it's the height of the box, but we can translate this h, kind of this line segment that is of length h, to like maybe here. So the distance from the top of one of the smaller spheres, that's not what I meant to do. So we can also think of it as a distance from the top of one of the smaller spheres to the distance to the bottom of one of the lower spheres. So this can also be described as h. And we also know, let me just mark this in blue this time, I hope that's blue. We also know that the distance from the center of one of these smaller spheres to the top or bottom of the box, depending on which sphere you're looking at, is of length 1. And we know that just because the problem states that the smaller spheres are each tangent to 3 sides of the box, and one of these faces is going to be the top and the bottom. So really what this problem, all that's left to find for this problem, and what it's really asking for, is this length right here, this white segment right here. So now we can go over the problem solving strategy that I wanted to go over, and that is connecting the centers of tangent spheres. Now I know this strategy might be kind of obvious, maybe you guys have been doing it since your first contest, or maybe even before your first contest, but I think it's definitely very powerful for how simple it is. So let's go and connect the centers of these spheres right here. Oh, that's not straight. Let me just redraw that, hopefully get it right this time. And we can draw centers, connect the centers here and here. Okay, well, I don't really see anything quite yet, so maybe what I can do is think about a connection from here back here to this, if we look at it from the top left sphere, and we can think about connecting this sphere right here to the center of this one right here. Oh no, please. Okay, let me just redraw this. There we go. And then let's connect it right here. Okay, so we have a pretty interesting figure. We have something that kind of reminds me, at least, of a pyramid. So why don't we go ahead and just connect all of these to the center right here. So now what we have is this pyramid. And well, how does this help? Well, if we think about it, the height of this pyramid should end up being the height, half of the height of this unknown length that I mentioned at the beginning of the problem. And the truth is, we know pretty much the side lengths of every single, length of every single edge of this pyramid. And that's just because we know that these spheres are all tangent to each other. So we can say that, let's just draw the pyramid out here real quick. Can I? Yeah. So let's just draw the pyramid here so that we can have a better look at it. There we go. We have some central point up here. And there we go. Alright, so we have our pyramid, although it's probably not drawn to scale, doesn't quite matter. So we know that the base of this pyramid is a square because all of these spheres are tangent to each other, and so they should all have a length of 2. Hopefully that is pretty clear because, well, it's going to be the radius of one of the smaller spheres plus the radius of another small sphere. And we also know that the lengths of these edges right here that are pointing to this to the apex of the pyramid is going to be of length 3. And that's just because it's going to be the radius of one of the smaller spheres plus the radius of the larger sphere. Okay, so and our goal is to find the altitude of this pyramid. So let me just try and draw that right there. Cool. We'll call this length B, right here. This is B. So, well, how are we going to go about solving this? Well, the first thing that I want to point out is kind of drawing a segment from the center of the square to one of the edges, right? Oh no, it's not quite there. Alright, there we go. So we know that this length should be 1, and I hope that's pretty clear. It's going to be half of the square's length, which is 2, so this should be of length 1. If it'll let me write a 1. Cool. So what exactly do we need? Well, in order to use Pythagorean theorem, we might think of that because there might be a right triangle here somewhere. We need to find the slant height of this pyramid right here. So, maybe I'll mark it in red this time. I hope that's red. And we're trying to find the slant height of this pyramid. So, how are we going to do that? Well, that's not terribly difficult because we can just imagine that we're looking at one of these triangular faces of the pyramid, and the slant height should be the altitude of the triangle. So let me just go ahead and try and draw the triangle here. One of the triangular faces like this, like that, and I'll mark the altitude in red again. Can I move this way? No, I can't. Okay, so like I said, like we mentioned in the diagram, we know that this length that's not the pencil. This length is 3, and since this entire length is 2, and this is an isosceles triangle right here, we can say that this length is 1, and this length is also 1, and that this is, like I said, an altitude, therefore this should be a right triangle. And we can use Pythagorean theorem to find this length. We'll call this length A real quick. So we can say by Pythagorean theorem that a squared plus 1 is equal to 3 squared, or 9. So from there, that kind of looks like my A anyway. From there, we can say that a squared is equal to 8. Cool. So our plan was to use Pythagorean theorem again on this, using the slant height, half of the length of the square. So let's just leave a squared as a squared, not solve for a, because we don't have to. And we can just imagine this this other right triangle that we have right here. So let me draw that out real quick. We have our length a, altitude here. Then we have another. We have this 1 that we mentioned, half of the side length of the square base, and then we have the altitude b that we are trying to find. So we can say that, we can say that 1 squared plus b squared, which is what we're trying to find, is equal to a squared. Or that, or we can substitute a squared with just 8. And from there we can say that b squared is 7, and from there we can say that b is the square root of 7. So this basically finishes the problem because, like I said, the height of this pyramid should be half of this unknown length that we had at the beginning. So, and we can just add on 2 of the radii of the smaller spheres, as I said at the beginning of this video, so before we even looked at this connect the center strategy that we came up with. So, now what we can do is we can say, well, the height, oh no, the height of this can be, the height of this box, h, can be described as 1, the radius of one of these spheres, plus 2b, which we've now labeled this as, plus 1, or the radius of another sphere, so of another of these smaller spheres. And we can substitute this to say it's 2 plus 2 root 7, and that is h. And so we see that the answer is A right here, and we are done.